Let's turn our attention now to supercell thunderstorms. Now, supercell thunderstorm is different from a multicell or an ordinary cell thunderstorm in that this is a very large, long-lasting thunderstorm with a single rotating updraft. The rotation is one of the differences here. Multicell and ordinary cell thunderstorms do not have a rotating updraft, but a supercell does, and that's one of the reasons why the supercell thunderstorm is so long-lasting. Another difference is that there's very strong vertical wind shear. Um, when you have a downdraft, the downdraft hits the ground and then spreads out. Usually, you saw that with a multi-cell thunderstorm, the downdraft cut underneath the updraft. With a supercell thunderstorm, that's never going to happen. You're going to have the rotating column actually at the center of the storm, and then with a wall, what's called a wall cloud right around it, and the downdrafts come down and go outwards away from the center of the storm. We'll talk about how the supercell thunderstorm is formed. We'll talk about the rain-free base and the low-level jet. And we'll look at what a supercell thunderstorm looks like, or at least the conditions for a supercell thunderstorm at multiple layers of the atmosphere. This is what it would look like. We're looking at the very center of the storm. The storm itself is much, much bigger. In fact, relatively speaking, you looking at this storm right now, there have been some thunderstorms that would have had this updraft that you see in the picture right now, but the storm itself would be the width of the room you are sitting in. So yes, these can get to be really big storms. What you see is a rotating updraft, and yes, this one's starting to form a tornado in the center. This is the type of thunderstorm that forms the most severe types of tornadoes. We'll save that for when we do our video on tornadoes. But the rotation of the updraft itself decreases the pressure, thus allows a cloud to form right around that rotation. That's called a wall cloud. This is a wall cloud. It's the wall of your updraft. So how do we get a supercell thunderstorm to form? Well, you need very strong vertical wind shear. Let me show you the conditions that allow this vertical wind shear to happen. So here at the surface, you have, remember, a low pressure with a warm front and a cold front and a warm sector in between. This is the early stage of a mid-latitude cyclone. This is the area right here where you're going to develop the updraft of your supercell thunderstorm. Let me show you how this works. So you have cold air coming in to the cold front and warm air moving up to the warm front at the surface. Well, this is warm, humid air, generally from regions like the Gulf of Mexico. That's where supercell thunderstorms tend to form the most here in the United States, is the Great Plains with warm, humid air coming from the Gulf of Mexico. And so if you look just above the surface, about the 850 millibar level, you get something called the low-level jet, a very strong current of warm, moist air close to the surface. But above that, about the 700 millibar level, you've got cold, dry air coming from over the Rocky Mountains, from our upper level trough. Here's your trough. That is strengthened with a jet stream on top of it. Okay. So we have warm, moist air coming from the south in the lower parts of the atmosphere, and cold, dry air coming from the west in the upper atmosphere. This allows two things to happen. First of all, warm air beneath, cold air above, you generate instability. So you've got some rising motion, you're ready for an updraft. The second thing that it causes is very strong wind shear. So with this rising air, well, let's look at the wind shear first. You have air moving this direction, a different direction just beneath that, it causes a rotation of the air, causes the air to actually start to form um, a column of air that's rotating like so. But then because of the instability, it rotates it, so now it's a vertically rotating column of air that's moving upwards. So here it's a horizontal column of air, but then the instability turns it into a vertically oriented column of rotating air, which then looks like this inside of the thunderstorm. So you get a single rotating updraft that's going up, and remember that with air moving up, there's only a certain height that it can go. It reaches the tropopause, which is an isothermal layer, capped with the stratosphere, which is an inversion layer. So this is as high as it can go. So it forms an anvil, flat top, which we often say makes the cloud look like an anvil. But if this updraft is strong enough, it'll actually push through, and because of its momentum, it'll overshoot and go up into the stratosphere a little bit. And so you end up with a little bit of a bubble up on top. And then what happens on both sides, because of the wind shear, you get some entrainment that happens, creating a downdraft. Over here, you've got cooler air, creates a downdraft, and you end up with a heavy amount of rain over here. Very strong gust front, same as before. But in the region of the updraft, there's no rain at all. So you get your rain-free base around the updraft. And so often when people see tornadoes come in their area, they have very intense wind, very intense rain, hail, and then all of a sudden it's silent. It's very quiet. People come out of their hiding, and bam, there's a tornado right there. And so they're often told, you'll hear hail, you'll hear rain. When that stops, stay in place, because you've got a tornado coming right after that in the rain-free base. So here's another picture of the base of a supercell thunderstorm looking at the wall cloud. All right, there's your supercell thunderstorm. We'll pick up more on the supercell thunderstorm when we talk about tornadoes. Let's go a little more, though, shift gears a little bit to another effect that happens because of thunderstorms, and that is flooding. Flash flooding happens, well, flooding, of course, happens when it just rains and rains and rains, and you get floods. Here in Florida, we see that fairly often. That's why we have a lot of ponds around the areas, so that we have places for all that extra water that rains here in Florida to go. But occasionally, you'll get so much rain that ditches and canals on the side of the road, and even those ponds will fill up and overflow, flooding the roads a little bit. Yeah, no surprise about those types of floods. Flash flooding is a little different, though. Flash flooding, you get little to no advance warning, and it can happen from the tiniest of thunderstorms. What happens is you have a thunderstorm that parks itself, oh, I don't know, in this picture, maybe a couple 100 miles to the north or something, way up here to the north. And that you get a thunderstorm that passes over there, causes a little bit of erosion. Another thunderstorm that passes through the air, you get another bit of erode a little bit more, and a little more, and a little more every time the storm passes by. It's what we call training. We're training the ground, and pretty soon, instead of flat ground, you've got yourself a channel that all the rain can channel into one area. And that channel of water comes down into a region, a city, and can completely flood out the area. Now, areas such as out in the west, where you have lots of canyons, like the Grand Canyon or slot canyons in southern Utah, they're very well known, southern Utah, for slot canyons. But whenever you have those, a tiny rainstorm takes all the rain from the whole region, channels it into that one narrow area, and that water just floods any cities that are downstream of that one slot of that canyon. There were tons of floods in 1993 around the United States, that a lot of areas that were flooded because of flash floods. Just a handful of years ago, 2014, 2013, I think it was. You can look that up in the news. Boulder, Colorado had a really nasty flash flooding event. For a couple of weeks, they were flooded and couldn't really do much at all. Pretty bad situation. Okay, back to thunderstorms. Where do we get the most thunderstorms in the United States? Well, the most frequent, or the area that gets thunderstorms the most, is here in Florida. You'll remember back in Chapter 7 we talked about the sea breeze convergence zone. Well, here it is, creating the most thunderstorms. On average, you get over 90 days a year with thunderstorms in Central Florida. Here in the Daytona Beach area, we get somewhere in the high 70s on average. In the Great Plains, where we were looking at earlier, really not as many. It's fewer thunderstorms. But now on the next slide, I'm going to show you the average number of days per year where you get hail. Notice here in Florida, on average, we get less than 1 day a year. In fact, I've lived here in Florida for 8 years, and I can count on half a hand the number of times I've seen hail here in Florida, once or twice. So we really don't get that much here in Florida. And yet, we get a lot of hail in the Great Plains. Why? Why do they have fewer thunderstorms in the Great Plains and yet more hail events? Well, that has to do with the type of thunderstorms we develop. Here in Florida, we develop primarily multi-cell thunderstorms, so you have a strong updraft, which creates a lot of very heavy rainfall. But that updraft is generally not strong enough to produce heavy amounts of hail. But in the Great Plains, you have a supercell thunderstorm, where you have a really strong rotating updraft that is strong enough to hold blocks of ice that are the size of a baseball. And so you're more likely to get hail in the Great Plains because of the supercell thunderstorms that they produce.